Hello, students, and welcome. I want you to think about something for a moment. Almost everything around us, the air we are breathing, the milk we drink, the soil in the garden, is actually a mixture. But what if we only need one pure substance from that mixture? Well, today, we are going to become scientists and explore the amazing ways we can take these mixtures apart. Let's begin.
So, here is our plan for today. First, we will ask the most important question: why? Why do we even need to separate mixtures? After that, we are going to build our very own chemist's toolkit, step by step. We will start with some simple methods for separating solids, then we'll learn how to get back things that have been dissolved, and finally, we will look at some really advanced techniques that are used in big laboratories. By the end, you'll know exactly which tool to pick for the job.
All right, first things first. Why do we go through all this trouble of separating mixtures? Well, the answer is simple. We often need pure substances for them to be useful.
Just take a moment, think about the world around you right now. The air you are breathing. Is it just one single gas? Of course not. What about the water in the sea, or the glass of milk you might have had this morning? Are any of these things really one pure substance?
The truth is, almost everything in nature is a mixture. But very often, it's the individual parts, the pure components, that we really need. For example, we cannot drink salty seawater, but we desperately need the pure water from it. We can get so many useful things like protein and fat from milk, but first, we need to separate them. This is why separation is so very important.
So, how do all these separation methods work? There is one very simple but very powerful idea behind every single technique. We can only separate a mixture because its different parts have different physical properties. Maybe one part has bigger particles, maybe another part boils at a different temperature, or perhaps one is heavier than the other. Every method we will learn today takes advantage of one of these differences.
Let's start with the most basic tools in our toolkit. These methods are for separating things that do not dissolve in each other, like a solid that is mixed in a liquid.
Think about something very common, something that happens in almost every kitchen. When your parents make tea, what is the very last thing they do before they pour it into a cup? How do they get the tea leaves out of the tea?
Yes, they use a strainer or a sieve, which is a type of filter. This process is called filtration. It's a very simple method to separate a solid that has not dissolved in a liquid. You just pour the mixture through the filter. The liquid part passes right through the tiny holes. We give this liquid a special name. We call it the filtrate. And the solid particles, which are too big to pass through, they get left behind. We call this the residue. This is exactly how you could clean muddy water.
Now, this brings up a very important question. If filtration is so good at separating mud from water, can we also use it to separate salt from water? What do you think?
And the answer is a very clear no. This is a very important point to understand. You see, when salt dissolves in water, it breaks down into particles that are incredibly tiny, so small that they can easily slip right through the holes of the filter paper along with the water molecules. So remember, filtration only works for insoluble solids.
So this brings us to our next big challenge. If we cannot use filtration for dissolved substances, then how do we get them back? How can we possibly get the salt back out of salt water?
The answer is a method that I'm sure you have seen before: evaporation. It is very simple. First, we heat the solution. Now, water turns into vapor or steam very easily when it's heated. We say that water is volatile. The salt, on the other hand, does not turn into a vapor. It is non-volatile. So, as we heat the solution, the water turns into steam and escapes into the air, and what is left behind? The solid salt.
So let's summarize. When should we use evaporation? We use it when we want to get a dissolved solid back from a liquid, and we are not worried about keeping the liquid. The physical property we are using here is the difference in volatility. That is, how easily something can turn into a gas.
Okay, so filtration and evaporation are our basic everyday tools. But what about more difficult mixtures? Now we are going to look at some of the specialist tools. These are advanced techniques that scientists use when the basic methods just don't work.
Let's think about milk. As we know, milk is a colloid. The tiny fat particles are spread all through the liquid, but they are much too small to be caught by a filter. So how is cream or malai or even butter separated from milk or curd, both at home and in big dairies?
For this, we use a special technique called centrifugation. What happens here is that the mixture is put in a machine called a centrifuge, and it is spun around at a very, very high speed. Imagine a merry-go-round spinning extremely fast.
This rapid spinning creates a powerful force. Because of this force, the heavier, denser particles are all pushed to the bottom, and the lighter particles, like cream or butter, they float right to the top where they can be collected.
Now here's another interesting problem for you. Until now, we have only talked about separating solids from liquids. But what if you have a mixture of two different solids? For example, what if you mix ammonium chloride with common salt? How could you possibly separate them?
For a mixture like this, we use a very special property that some solids have. It's called sublimation. Now, certain solids, like ammonium chloride, do a very neat trick. When you heat them, they don't melt into a liquid. Instead, they jump directly from being a solid to being a gas. It's almost like a magic disappearing act. So if we heat our mixture, the ammonium chloride will turn into a vapor, leaving the common salt behind. Then we can simply cool down that vapor to get our pure solid ammonium chloride back.
Okay, and for our last advanced technique, let's talk about something very colorful. Did you know that a single drop of black ink is not actually just one color? It is usually a mixture of several different colored dyes. So the question is, how on earth can we separate these different colors from each other?
We do this with a beautiful technique called chromatography. The name literally means color writing. Imagine this. We put a small dot of ink near the bottom of a strip of filter paper. Then we dip the very bottom of the paper into water. As the water starts to climb up the paper, it's like a race begins. The water picks up the different colored dyes and carries them along. But here is the secret. The dyes that dissolve better in water will travel faster and farther up the paper. This difference in speed is what separates the colors, creating a beautiful pattern of different colored bands.
So, we have now collected quite a few powerful methods in our chemist toolkit. Let's do a quick summary so we know exactly how to choose the right tool for any mixture we are given.
Let's look at this table together. For something like tea leaves in tea, we use filtration because the leaves are insoluble. For salt dissolved in water, we use evaporation because of the difference in volatility. To separate butter from curd, we use centrifugation, which relies on a difference in density. Now look at this one, iron pins mixed with sand. For this, we can simply use magnetic separation. The iron is magnetic and the sand is not. A simple magnet will pull the iron pins right out. For ammonium chloride and salt, we use sublimation. And for separating different colors, we use chromatography, which depends on different rates of solubility. You see, every method is chosen based on a unique physical property.
And that really is the most important thing to remember from our session today. It doesn't matter what the mixture is. If its components have even one different physical property, there is a way to separate them. We just need to choose the right technique.
So I am going to leave you with one final challenge. We all know that oil and water do not mix. So my question to you is, what is the key physical property that keeps them separate? And now that you have your new toolkit, which method would you use to separate a mixture of oil and water? Think about it. Thank you for exploring the world of mixtures with me today.